Hello everyone. Welcome to my YouTube channel Chemistry Quest. This is the fourth lecture on biomolecules. In this, we will be discussing cyclic structure of glucose. So first, let me remind you the Fischer projection of glucose. It is represented as following. This is the carbon number 1. This is second carbon. This is third carbon. This is fourth carbon and this is fifth carbon. This is the Fischer projection. The vertical and horizontal line intersection point is the carbon atom, and there are four asymmetric carbons in the glucose atom. So what happened is some properties of reactions were not able to justify this structure of glucose. This is the Fischer projection. So there were some reactions which were conducted by scientists, and this molecule was not showing those reactions. So let's discuss that. So first thing is that the aldehyde group is present in the glucose molecule in the Fischer projection like the CHO 1, 2, 3, 4, 5, and this is a CH2OH. So this aldehyde group is present in the Fischer projection of glucose. But despite having the aldehyde group, glucose does not give Schiff's test and it does not form the hydrogen sulfide addition product with NaHSO3. This is the conclusion why this Fischer projection of glucose was rejected. So this was the first reaction that it, although the aldehyde group was present, but it does not show Schiff's test and it does not show any reaction with hydrogen sulfide. Okay. Now, next reaction is, as we have seen earlier that glucose forms pentaacetate when it gets to react with the acetic anhydride molecule. So this is the pentaacetate molecule, and to our surprise it is that this molecule does not react with hydroxylamine. This is NH2OH. This is hydroxylamine. This reaction also surprised scientists. So it indicated the absence of free CHO group. This is the second reaction. Now next, one more thing was that was very important. It was about structures of glucose. So glucose is found to exist in two different crystalline forms, alpha and beta. So we have to remember the condition of alpha glucose and beta glucose. The alpha glucose melting point is 419 Kelvin, is obtained by crystallization from concentrated solution of glucose at 303 Kelvin. This is about alpha glucose. And while beta form, that is melting point is 423 Kelvin, is obtained by crystallization from hot and saturated aqueous solution at 371 Kelvin. So we have to remember these conditions, that glucose exists in two different crystalline forms which are alpha and beta. So the behavior could not be explained by the open chain structure for glucose because of these reactions which we discussed earlier. So what was proposed by scientists was that it was proposed that one of the OH groups may add to the CHO group and form a cyclic hemiacetal structure. That was proposed. So how it happens we will see in the next slide, but how we have to remember that it was found that glucose forms six-membered ring in which OH at C5 is involved in ring formation. This was the conclusion, right? Now next, as those reactions explain that there is a CHO group is absent, which is free, and also existence of glucose in two forms as shown below, that is alpha form and beta form. These two cyclic form exist in equilibrium with open chain structure. So this is the open chain structure, open chain structure of glucose. So what happened is the fifth carbon atom has this OH group. So the lone pair on oxygen, it reacts and it attacks the electrophilic center of carbon, and finally it forms a hemiacetal structure. Hemiacetal. So what are acetals? Acetals are those compounds in which the carbon atom is attached to two alco- L OR groups. That is, this is the acetal. But what is hemiacetal? When it is containing only one OR group, that is hemiacetal. So now we have to remember an important thing is that what is alpha form of glucose and what is beta form of glucose, that we will remember from this particular structure only. So as I have already mentioned that the open chain of glucose has this fifth carbon atom in which oxygen atom on has electron pair which reacts with this carbon having electrophilic center. So it leads to the formation of two rings, that is hemiacetal structures. In one of the acetal structure, the first carbon, you have to see in both the structure alpha and beta, the first carbon OH is on the right side, and in the first carbon here beta OH is on the left side, and rest everything is same. Second carbon, third carbon, fourth carbon, fifth and sixth, every full molecular structure is same, but the first carbon is different. That is, OH is on the right side. As we have already discussed, that when OH is on the right side, we have to compare with glyceraldehyde, and it is D plus glucose. And when OH is on the left side, it is D minus glucose. But here one we have to think that there is another term known as anomers. So anomers are those stereoisomers which differ in the position of atoms only at the first carbon. Like I have explained that in alpha D glucose and beta D glucose, the full structure is same, but only the difference is at the first carbon. Sorry. If OH is on the right side, it is alpha, and if OH is on the left side, it is beta. This is known as anomer. Now, we know that the two cyclic form, that is a two cyclic hemiacetal form of glucose, differ only in the configuration of the hydroxyl group at C1 called anomeric carbon. Such isomers, that is alpha form and beta form, are called anomers. This I have already explained. Now next we have to see one more structure of glucose, that is the ring structure. So for ring structure we have to take a reference ring, that is pyran. So the six-membered cyclic structure of glucose is called pyranose, alpha or beta in analogy with pyran. This is the pyran structure. Pyran is a cyclic organic compound with one oxygen atom and five carbon atom in the ring. Now we have to use this molecule and we have to write glucose, glucopyranose structure. How we will write, you will see in the next slide. So what happened? So as we have seen earlier that in alpha D plus glucose, the carbon atom had a OH group on the right side and H on the left side in alpha form. And beta form we saw that OH group is on the left side and H is on the right side. So whatever is on the right side, it goes down. This is the rule. Right side, right side group goes down in the structure, goes down in structure representation. This is the rule. So if OH is on the right side, it goes down. So first carbon OH is on the right side. This is the alpha D plus glucopyranose. And here OH is on the upper side. It is not down, it is up. So this is beta D glucopyranose structure. The cyclic structure of glucose is more correctly represented by Haworth structure. is given below. This cyclic ring structure we have compared with the pyran ring. This was the pyran ring with one oxygen atom and two double bonds. So this was given by Haworth's scientist, and this whole structure is known as Haworth projections. They are the three-dimensional structures. So now let's revise whatever we have studied till now. So we have studied what is anomer. We have studied the reactions which the Fischer projection of molecule of glucose was not showing. And finally we saw the glucopyranose structure. And third thing we saw alpha and beta glucose. So this is the revision. So if you like the video, please hit the like button, share with your friends, subscribe to my channel and hit the notification bell for upcoming videos. Thank you and have a nice day.